Okay, cool. Hi. Let me get started. Oh, I used the wrong loading screen. Whoop. If it said April 2023, it's not April 2023, it's June. Um, but that's just me demonstrating that this is, you know, what do you call it? A real live stream. We're not AI. I insert like a what do you call it? A fake an Easter egg testing the community. What did Emily do wrong this time? But anyways, let's roll it all back, guys. Welcome to I guess Linea's June community call. Today we are joined by Ivo and Julien from the Linea team. And we're just going to go over, what's new for Linea in June, as well as just kind of what's happening behind the scenes. So, Julien, you can hop off for now after Ivo starts. But yeah, if you guys want to just say hello, and then I'll kick Julien off after just bringing you back on. Wow, this is really awkward. Okay. Let me roll it back. I got distracted because I made a mistake, and now I'm just like, oh. Okay. 3, 2, 1. Hi guys, I'm Emily, I'm the developer advocate for Linea, and today we're excited to bring on two wonderful engineers from the team. Ivo, please introduce yourself.
Hi everyone. Hi, good morning, good afternoon, good night. So I'm Ivo. I'm a research engineer at Consensus and working on Linea on gnark.
Cool.
And hey guys, Julien here, head of engineering, so working on Linea. I've been in Consensus for a couple of years, and yeah, happy to talk to you.
Yeah. Okay. Cool. So we're gonna start off with Ivo to come talk about gnark. Julien, I don't know what time it is for you guys, if it's like lunchtime or evening time or whatever, but I'll kick you off. And we'll bring on to talk about gnark. I'm not super knowledgeable about it, so I'm just gonna let you take it away. I believe you prepared a presentation, right?
Yes,
Okay.
hopefully you can see the presentation.
Cool. Let's get started.
So, hi. Hi again. So I'm Ivo. So today I'm going to talk about snarks and like what they are and why do we need them, and how it connects to Linea. So first of all, so let's say if we usually if we are executing like some kind of programs, so what happens is that like we have the program code and we have like some kind of like input to this program, and when we run this input on this program, like usually we get like some kind of output, and like that's it. So we have to trust that like this program has run correctly, and like everything has been computed correctly. But like sometimes like we want to do it like in a different way. So for example, let's say sometimes we do not want to reveal like what are the inputs to the program. So let's say maybe the input is some kind of trade secret, or like maybe it contains some kind of like private information, but we just cannot reveal. So and we cannot rerun like this program like to see like how it works. Or maybe let's say maybe the program itself it is like very complicated. Let's say it is a program like which factorizes some very difficult cryptographic problems, and like it just takes like maybe days or weeks or months or even years on like very high-end computers like to compute the answer. So but we still want to show that like this program has been has run correctly, and that's why for that like we may want to use like something called verifiable computation. And so like the idea of verifiable computation is that like we can create a proof of running a program correctly, and without revealing without having to rerun the program again, or without having to reveal, let's say, all of the inputs to the program. So we can selectively decide like what kind of inputs we want to reveal. So for example, let's say what kind of problems we want to solve. So as a very primitive example, let's say like we know let's say a solution to RSA factoring challenge. So RSA factoring challenge is that there is some integer and which is a product of let's say 2 primes. And actually like there are like challenges out there that like if I can factor like this large integer into like this into this primes, then I can like claim like some kind of prize, like prize money, maybe $1 million or whatnot. And but let's say like if this verification program like if it runs on Ethereum, so I do not want to reveal my inputs because like someone could, for example, like front run my let's say result, and they can just claim the input like on my before me, or like who has actually like done all the like expensive computation. So that's why I would prefer to use it like or I want to prove it like in a verifiable manner that I know the inputs, but I do not reveal the inputs right now. I will reveal the inputs like after I have claimed like let's say the prize money. Or let's say maybe we want to perform let's say privacy preserving like Ethereum transactions, where like we can show that like some transaction is valid without revealing who like actually like who signed the transaction, but we can still verify that like this transaction is verified or signed by someone, or maybe like we can put like some kind of like additional attributes on the account, like who has signed this transaction. So for example, like it has like some kind of age, or maybe it has performed some transactions in the past, or like over 1 year, or something else. Or for example, we can like we can extend like this example having like, let's say not even private, but let's say or not anonymous, but also like private transactions. So like we can construct a zero knowledge proof that like some transaction, like we have received some kind of transaction by a valid account, but we do not reveal like what is actually the transaction. And so we just post, for example, the difference, or let's say the state root delta. And then everyone can verify that yes, like there was some transaction, the state root like it changed, but they do not see like what is the transaction. So for example, let's say we want to build like some kind of private DEX, or like a private swap or something else. Like extending on this idea. So there's also like, let's say, some inherent limit on the number of transactions what we can perform within an Ethereum block. So like right now, like the factor which limits the number of transactions within a block is the available gas like within a block, which is like 30 million. And so like if you know that like one transaction is like about 21,000 gas, so like the number of transactions which can be performed, like it's limited by, let's say, 1,000 something. And like this is essentially the limit of Ethereum right now. So we can perform 1,000 something transactions per every block, every 12 seconds. But like if you would like to like scale Ethereum infinitely, so we can actually like we can also construct the zero knowledge proof that we have let's say 10,000 or like 100,000, 1 million transactions, which are all valid and which result in state root delta. And we can construct the proof that like all these transactions are valid. So like this essentially it would allow infinite scaling. Of course, like assuming that we have like let's say efficient enough proving schemes, efficient enough like prover machines, and so on. Or for example, what we can do, like we can also construct like some different kind of statements. We can show that I have stored like some kind of like let's say some amount of structured data. So I have 1 terabyte of data which has some kind of structure. For example, they are some kind of powers of DAO, or they contain some kind of information, and I can construct like this proof that yes, like this is valid. And so like essentially, let's say this proof of storage, like this would allow to extend, like not Ethereum, but let's say for example, like to define some kind of like neo consensus like consensus algorithms, like which depend on the proof of storage. And so we can do them like there are known ways like how to construct like these kinds of like zero knowledge proofs. They are called SNARKs, and they are, I would say, quite well studied, quite well known. And so what is gnark? So gnark, it has, I would say, it has 3 aspects which are related to it. So the first aspect is that it is S, so it is a succinct, meaning that the proof, like it has to be relatively short compared to the statement, or like let's say to the program what we want to prove. So like usually we require that we require that let's say the length of the proof is logarithmic, like in the size of the statement, meaning that let's say like if the size of the statement is 1,000 something elements, then the size of the proof is like 3 elements, or like if it is 10,000, then it is 4 elements, and so the size of the proof, like it grows I would say very slowly compared to the size of the statement itself. Secondly, like it has to be non-interactive, meaning that it should be possible for the prover to construct the proof, and then like everyone should be able to verify it. So like there is I would say 2 different paradigms. One paradigm is like being interactive proofs, and another paradigm is non-interactive proofs. But I would say the interactive proofs, like they have like some drawbacks. So the first drawback is that like it is interactive, so like it requires some kind of communication between the prover and verifier, like online, and like essentially like it requires both being online at the same time. So it means that, for example, the prover cannot create the proof for let's say for the public, or the prover cannot broadcast the proof, because like if you would do that, then we would have to trust that the verifier, like some verifier, like which is who is running this interactive protocol, like they have done all the steps correctly. They haven't let's say colluded with the prover. It also allows to like verify some proofs like in the future. So let's say like if you have like some historic block like which contains some synonymous like SNARK proofs, then we can verify them in the future that it like they are valid, and like essentially ensuring that the whole let's say chain of trust, or like let's say the chain of blocks, like everything's valid. And finally, it has to be argument of knowledge. So there are, I would say, 2 distinctions. One is argument of knowledge, and one is let's say argument of possession. So argument of knowledge means that I need to have, like I need to know like what I'm proving. So for example, like thinking about smart cards, or like let's say thinking about like some kind of like hardware wallets. So like usually like I do not have access, or like I do not know what is the secret key within this hardware device, so I only have access to it. So I can send some transactions to sign, and it signs them, and then it sends the signed transaction back. But like it doesn't prove that I really know the private key. So that's why I need the argument of knowledge. So I need to be able to extract like this secret value from like either from the hardware device, or like I just need to know it like somehow. And for example, like there are different proving schemes, or like proving systems, like which allow to construct these kinds of snarks. So there is Blanc, there is Cross16, there is Halo, and like nowadays, like people are researching and proposing like new approaches for constructing snarks. So some approaches are, for example, they have smaller proofs, or some have, let's say, have more efficient verifiers, but like the prover has to work more, or maybe the prover has to work less and the verifier has to work more. So like there is a lot of different, I would say, considerations, or like different parameters of what we can choose when we choose the proving system. But what connects like all the different proving systems is that like usually they are, I would say, very mathematically primitive. So like right now I'm talking about on a very high level statements what we want to prove, but actually like let's say the snarks, they are some relations between different polynomials, and so constructing these polynomials by hand, let's say for complex programs, like it is actually it's very difficult. So let's say like we would have polynomials with degrees, or let's say the power of the highest monomial within the polynomial, it is in the millions. So it would be impossible to construct it by hand, or even if you would have like some kind of like helper tools, it would still be difficult. Like for example, if you want to compose different parts of like, or let's say the different modules together, like into some bigger program. And for that we have gnark. So gnark, essentially it is a framework for developing snarks. So, and gnark, it is a Go package. So essentially when someone wants to write a program and verify it in zero knowledge, then what they have to do, like they just have to import like some Go package, and instead of doing, let's say, native operations, they use the gnark API like to define the operations. So the gnark API, like let's say the low-level API, it only provides I would say very basic primitives, so addition, multiplication, subtraction, division, inversion, checking that two values are equal, and so on. And to make like the user experience easier, we have built on top of these basic primitives a lot of I would say this tools, or let's say standard library on top of that, like which allows to do like, let's say, operations what we care about in real life. So for example, the operations what we care about in real life are checking the validity of signatures, hashing some values, computing the hash value, computing Merkle trees, performing like some kind of like non-native arithmetic, computing let's say PLS signatures, and so on. So like we like in real life, we're interested in practical cryptographic applications. And also like gnark, because it is essentially it's only a Go package, so it doesn't require like any kind of domain specific language. So for Go lang users, it should be like very easy to start with. So they just download the package and start using it. So in addition to allowing to define these programs to be checked in zero knowledge, gnark also allows to like generate all the proving keys and verifying keys, or perform all the pre-computation. We can do it in a trusted manner, or we can do it in using a multi-party computation manner. So meaning that like we can generate this pre-computation data without having to trust any single, let's say, entity when generating this pre-computation data. gnark can also like construct, let's say, create proofs, and gnark can also verify that the proofs are valid. And gnark allows to output both the, let's say, native verifiers and also like smart contract verifiers. So and like they both have like their own uses. So the native verifiers, like we can use them, let's say, for integrating gnark or zero knowledge proofs into, let's say, traditional web services, for example. So let's say, for example, we want to extend some authentication mechanisms with zero knowledge, showing in zero knowledge that like the user has some kind of attributes, then we can just integrate like with gnark quite easily. Or if you want to use, let's say, if you want to verify something on chain on Ethereum, then gnark can just output the Ethereum smart contract verifying the proof, and it just outputs if the proof verified or not. And like then the, let's say, the actual dApp can like act on this information if the proof verifies or not. So example applications, we have mostly like gone over the application, but we can use like snarks to construct zk EVMs or zk VMs, zk rollups, for example, consensus rollup, or like zk BNB, or for example, Binance used gnark to give proof of solvency, or for example, like constructing trustless bridges between different chains. So in a trustless bridge, we can prove in zero knowledge that like some, let's say, some smart contract like on one chain received like some kind of like funds or transactions, and then like this proof can be verified like on other chain, like to release the same funds, and and allowing bridging like the assets between like the different chains. gnark also provides, let's say, these low-level primitives for cryptographic applications. Like if you are not interested in like zkSNARKs themselves, but only like you want to perform like some kind of, let's say, computation. So for example, gnark crypto is used in the original Ethereum client, execution client, or it also was used like for the EIP 4844 ceremony, like to generate like this, let's say, the pre-computation data necessary for the EIP 4844, and also like in other applications. And like essentially possible applications, they are limitless. So it's just come up with like some ideas, and you can probably use gnark like to do it in zero knowledge. And of course, gnark is used in Linea. So like So gnark is used in Linea, I would say, in 3 stages. One stage where gnark is used is to prove the correctness, or let's say prove the precompile or calls to precompiles in Ethereum. So in Ethereum, like usually, like what we have is that like there are like some kind of like opcodes, like which define like the execution of of a transaction, and there is also like precompiled contracts which are used for, let's say, more complex cryptographic operations. For example, verifying ECDSA signatures, or computing pairing on PN254, and also for some elliptical operations. And so for that, in Linea, we use gnark, because like essentially gnark already has like these primitives, and it is more efficient to do it like in gnark. So how it works in general is that like we generate the proof of like this precompile calls in gnark, then we output this Plonk proofs, and then Linea, let's say let's say the Linea proving system, like it verifies this Plonk proofs. Secondly, where we use gnark is to compress, let's say, this lattice-based proof in gnark. So let's say the size of the proof of let's say the transaction block proof, like it is a square root in the number of inputs. So it is not, let's say, it is not succinct like in its definition. But what we can do is that like we can verify this proof like in gnark, and we can obtain like actually like a succinct proof, like what we can verify on Ethereum. And of course, gnark is used to generate this smart contract verifier, like which is finally posted on mainnet for verifying the rollup proof. And gnark is fast, so we have like ran some benchmarks. So like this benchmark is about like this is like essentially a Tamme circuit where we just wanted to compare like how gnark performs against other well-known SNARK proving frameworks, and like we can see that like gnark is, let's say, 2 times faster than other alternative Circum, and also like several times faster than ArcWorks. If you look at let's say, if we look at the more practical applications, so for example, proving knowledge of SHA-256 pre-knowledge, then like we see that like gnark is the fastest SNARK. So like actually like there is some other proving system which is a bit faster, but it is based in SNARK. So like there is I would say there is difference between like these zero knowledge proof systems. So SNARK like SNARKs, they usually have like slightly, let's say, slightly longer proofs. So and like this is factor like which like the users usually have to like when verifying something like on chain, so it is it may be more more expensive to verify, or it may not be. So it like it is per case to figure out like what's best approach. Or for example, like if you just want to perform let's say some cryptographic operations, then gnark provides this let's say these low-level primitives as a public interface. So, for example, we can also see that gnark is fastest when computing multiscalar multiplication on PLS12 384. To get started with using gnark, so the repository is available at gnark.io. The docs are available at docs.gnark.io, and we have the playground play.gnark.io, which I show a bit later. But essentially, to start integrating gnark into your Go program, you just have to add gnark dependency. So for that, you do go get gnark, and I recommend for development purposes, I recommend using like the development branch, because like development branch has all the latest optimizations, all the latest upgrades, and like it is usually several times faster to prove than using gnark on the main branch. we definitely we are backporting all the upgrades from develop branch to the main branch, but because I would say assets are at stake, we want to be really careful. So we are quite conservative when releasing new versions of gnark. So how to start with defining circuits is we have 2 steps. First, we have to define this type, which defines what are the inputs to the program. So in this example, I have this pairing circuit structure, which has the inputs P, Q, and expected. Where expected is, I would say, the public input, what the verifier can check, against what the verifier already knows. And P and Q are the private inputs of the prover. And secondly, we have to define the program itself. So we only have to define a single function or a single method called defined, which takes this API, let's say, type as an input and outputs an error. So as an example, in this example, we initialize let's say this standard library gadget, which allows to compute pairings inside the circuit. Then we compute the pairing for this private inputs, and then finally we check that this pairing equals to some expected value. And in this case, I didn't check the errors, but I always should check errors. I should return errors when they happen. And finally, if all's good, I return 0 error. To test that this circuit is defined correctly and if it works, I first I can use standard Go testing framework. So I just write the testing function, which takes in this testing T type. Then I initialize gnark testing, let's say, framework. I generate the data, let's say. I generate the data natively, using, let's say, gnark crypto or some other means, or IT serialize some data, or I import them from some transactions, whatnot. I define the circuit I want to check against, and then I give this input, and then I check that is the circuit correctly defined, if I can prove it, if I can verify it, if I, for example, we also have integrated fuzzer. If I try to change the inputs and I want to see that then the proof doesn't verify anymore. Or if I want to, let's say, use it without this testing framework, then I can just compile, create the pre-computation data, prove and verify without using this framework. gnark right now supports Cross16 and Blanc backends, because they are, I would say, most widely known and most widely supported by, let's say, alternative frameworks out there. We also have the playground. So the playground is available at play.gnark.io. So the playground allows to, let's say, to try out gnark. It works. What are, let's say, different example circuits? So previously I talked about let's say this RSA challenge. And let's say we want to write a circuit which checks the validity of the RSA challenge. So I have 3 inputs to the circuit. So this is the RSA challenge, which is known, so it is public, and I have 2 private inputs, P and Q, what the prover knows. So I have the define method, and the define method first I check, I multiply the inputs together to get let's say the product of prover's input, and I check that this prover's input is correct. But what we have to care about is that we do not under constrain the circuits. So if I would have only, let's say, this part of the program, then actually the circuit will be under constraint, because another valid input will be this product times 1. But this is not actually this is not a valid input. So I have to enforce that the inputs are not 1, and now I get fully constrained circuit. And so if I run this circuit, so let's see, like it compiles it into this polynomials, and like it shows that everything is correct. So let's say like if we try to like change the prover's input, like if the prover like fakes the input, like what happens? Like we cannot construct this proof, and like this is like that actually like this is what we want. And gnark also shows that where is this problem. So the problem is here, like that like this equation doesn't hold. This corresponds to this line like in the program code, and like we can debug like if anything is incorrect, for example. So let's change it back, and now the proof is valid again. Okay, that's great. One more aspect, like when writing like let's say SNARK like programs, what we want to verify in zero knowledge is that like if we write, let's say, very big, very practical applications, then like actually like this RSA, like RSA, it was a toy example. So actually like it will consist of like, let's say, 1,000 different checks here, like some checks there, like we compose different components together, and like in the end, like let's say the program what you want to verify, it may be very big, and it may be very difficult to construct a proof for. So that's why gnark has also like built-in profiler, like which allows to show like where actually the complexity comes from. So in this example, so in this example, I constructed a profile for a pairing circuit. So a pairing is some cryptographic operations which is like used to, let's say, recursively verify different SNARK proofs, and like. And what does it consist of? So a pairing consists of like two, let's say, sub processes. One is the final exponentiation, and another one is Miller loop. We can see that like if the full pairing takes like 340,000 constraints, then the final exponentiation takes 165,000, and the Miller loop takes like 176,000. So we can zoom in into, let's say, other places, and to see like where this complexity ends up at. So, and we can see that actually like all the complexity ends up at like this mul mod subroutine, like which performs modular multiplication in non-native arithmetic. And so actually like if you would want to I would say if you would want to optimize the prover time, then it makes most sense to optimize like this particular routine, like in the program. So, and for example, like if we just optimize this one, then like essentially it automatically like makes everything faster, like it makes the prover faster. And like to wrap it up, so what are our plans for the future? Of course, we want to make like everything faster. So the problem like with the SNARKs, or like creating SNARK proofs, is that they're relatively slow compared to computing the, let's say, the programs itself. So let's say like if you want to do ECDSA verification, like it most probably takes like less than 1 millisecond, but constructing a SNARK for that, like it takes on the same machine, I would say like a few seconds. So so there is a considerable difference in running the programs natively, or creating the proofs for these programs. So for that, like we are looking into like, I would say, different means. So we are looking into patching, we are looking into folding, we are looking into carrying proof data, like everything, like whatever helps to make it like more faster. So it's I would say it is an aspect of making everything faster programmatically, and also like making algorithmic changes like to gnark, and coming up or like implementing more efficient proving systems. We are also very worried about robustness, correctness, and soundness, meaning that like we want to like really ensure that when the users write programs, that they are that they are not under constraint. Like as we saw in this RSA example, it is very easy to construct like a program which is under constraint, and then essentially this means that the prover can provide like false inputs, and we want to avoid that. So we are looking into like formally verifying circuits, verifying that like all the operations are correct, that there are no constraints, or like there are no variables which are like unchecked, or maybe also annotating like some methods which ensure that like there is, let's say, mathematical correspondence between like some mathematical statement and also like this and this program. We want to make gnark, let's say, more user friendly. So we are looking into, like, we are asking for a feedback, like how to make the user interfaces more like user friendly. What are, for example, what are the standard gadgets what we should implement, like what would make gnark more user friendly. We are also looking into like implementing GPU and FPGA acceleration to make the prover faster, and we are also looking into like making gnark more compatible with WebAssembly. So right now, gnark programs can be compiled into WebAssembly, but it is not fast because we are using code reflection like here and there, and this is very slow when done in WebAssembly. And that's it. So thanks for listening.
Wow, that was a lot. Okay, so how about let's play this back. So assuming someone didn't come in at all, like they came late, right? And we had to answer, gnark in 5 minutes. First off, what is gnark?
Gnark is zero-knowledge proving library.
$0. Okay, cool. What is the difference between gnark and gnark crypto?
Yeah, a good question. So actually, like gnark crypto. Like when building a SNARK, so we rely on let's say cryptographic primitives, on finite field arithmetic, on elliptic curve arithmetic, and so on. So gnark crypto provides all of that, and gnark uses that. And like essentially, gnark crypto, like it is separated. So for example, if someone wants to use this very fast implementation of these cryptographic primitives, then they can do it like without having to import gnark.
Okay, cool. For somebody getting started with, or what's another question you might ask in 5 minutes? Okay, so what is gnark? Difference between gnark and gnark crypto. How is gnark used at Linea?
Yeah, so gnark is used at Linea in 3 stages. One is to show the correctness of like to prove the precompile contract calls. Then to, let's say, to compress the proof into a succinct proof, like which is posted on Ethereum, and also like to generate this verifier for like which is then let's say put on Ethereum, like which verifies the correctness of like of Linea. I'm sorry.
Yeah. Okay, and then what makes gnark different from like other libraries?
So one thing what makes gnark different is that we do not have like this DSL, domain specific language. So everything like gnark programs are Go programs. So for example, like there are like different the other frameworks, for example, Circum, like which has like its own DSL. So it's a whole like a language, or there is a Noir front end, like which allows to, like it is I would say Rust like let's say language, like for writing the circuits. But like this means that like all the tooling has to be like the user has to install like all the separate tooling, like get everything to work, maybe like compile like different components and put them together. So like for example, like for Circum front end, you can have like this rapid snark backend, and so you have to compile like different components together. So gnark provides everything from end to end. So like it provides the front end, the back end, the verifier, the prover, like everything. So it's, I would say, one code tool.
Okay, cool. And then with regards to like speed, how does gnark like make itself? So that's like user experience side, right? Gnark compared to other libraries, but like gnark, right? If I remember correctly, like won the award for being like the fastest mobile like library. How?
Yes. So I would say gnark. So gnark, I would say like it depends on the benchmarks, but like on some of the benchmarks, like gnark is the fastest on like on mobile, on like on native, on PCs, on Macs. But I would say this depends on like on the benchmark. So, but in a lot of benchmarks, gnark beats the other frameworks. But like there is subtle difference.
Okay, cool. And then outside of Linea, popular use cases or applications you've seen gnark used in?
I think like yeah, like I was like I quite like the Binance proof of solvency. I also like different trustless bridges. And I also like let's say using smart crypto for for example for EIP 4844. So like this data availability in Ethereum.
Okay, very cool. That was good. gnark in 5 minutes. Thank you so much, Ivo. That was awesome.
Okay, thank you.
I'm gonna, I guess what you say, kick you out and bring on Julien. But thank you so much for joining. That was really
Yep.
fun.
Yeah,
Have a
thank you.
good rest of your day.
Okay, thank you.
Cool. Hello, hello. If you were there the
Me.
whole time, kudos on you. That was a very dense topic. But
Yep.
yeah, so I brought on Julien. So we talked a little bit about Linea under the hood. Now we're gonna kind of talk about Linea, not necessarily moving forward. I guess this is based on the updates that came out earlier this month, right? We're talking specifically like message service, SDK. I think Julien, you said you might have prepared some slides if you wanted to go over it, but just talking about what Linea can do for you in the future / now.
Yep. I will do that. Let me see how sharing works with this tool. Okay. I think that's it. Can you see my screen? Yes, you can.
Yes.
Cool. So actually, what I'm going to do is to show a bit the current state that we have and what's in progress, what's coming soon, because we have a few pieces that are coming soon, and actually the SDK is coming soon. It's not yet released. So yeah, that's what I'll start with. So if we look at the bridging and message service layer that we have, here is a quick picture to help you represent a bit the different components. So here you can see the main rollup message service contract, which has two main purposes. First is the rollup, so it holds the state and verify the state. So inside you will have the gnark verifier specifically that verifies the zero knowledge proof. And you have the message service. The message service is almost the same than what you have on the other side. It's responsible for transporting messages from layer 1 to layer 2 and from layer 2 to layer 1. With this new big release, the alpha release, we have decided to split the message, like the transport layer, into two main pieces. The first is the anchoring, and the second one is the execution of each message individually. We've done that mostly for reliability reasons, to keep responsibilities really clear. The first one is to anchor messages to prove that they are correct, and then the second one is to execute them, which gives more flexibility in the different ways we can offer this second service of message execution. And that's where we'll have some deep dive, basically. The first one, just quickly, is the anchoring. That's part of the top level part here. It's managed by the coordinator, which instruct the sequencer how to process as well. And the coordinator finalize blocks on layer 1. That's the one that is sending the block and the proof with the data availability, transaction, etc. And it also anchors message hashes that are coming from layer 2 to layer 1. As well, on a regular basis, the coordinator takes a few message hashes that were anchored by user on the message service and write them on the message service on layer 2. And then we have the execution workflow. The execution workflow basically waits for a message to be anchored on the message service. And once this is done, will get the message input on the left side and will send it and execute it, trigger the execution, pay for the main gas fees of this message on the destination layer. This works layer 1 to layer 2, like you can see on the arrows, but as well on the other side. Very similar. And we have two ways to do it. Either you put a fee in the message. In this case, it can be like if the postman estimates that there is a bit of like enough fees, it will get the fees and process your message. Like process your message on the message service, so it's processed automatically. In the current state, this is what is done at the moment, and we are not enforcing any fees. So that's why if you have used the guide on EtherScan, for example, to bridge, it's done automatically. You don't have to do anything, which will change in the future. But I'll get to that part later. The second big leg of the flow is like the second option alternative is if you don't put fees. In this case, you can either claim the fee manually, and there won't be any fee incurred. The only thing is that you need some native ETH on the destination layer to be able to claim. And the second sub leg is like if a protocols embed automatically the way to claim messages for you to execute transaction for you. So if I summarize a bit the flow, we have a user that's sending a message. The coordinator is going to anchor it on the message service. Someone, depending on the fee policy that you've decided, will execute the message for you. And you will receive either your native ETH or the ERC20 or any more complex workflow. Can be anything basically, because it's completely arbitrary messages, so you can implement any lock on min, burnt on min, any kind of things on top of this layer. That's really a tool for partners to build. So summarizing a bit on the use cases and how you are hinted to claim fees in the future. So to bridge ETH, native ETH, at the moment we recommend to either use partners or the EtherScan documentation. I've added the link here. The only fee that is required is for the exit, layer 2 to layer 1, with a super tiny fee. Looking like probably next week, I hope, we should have a UI, a bridge UI, where you will be able to claim, like to trigger a transfer and to claim the message automatically if you haven't set a fee, or to put a fee that we will suggest for you, and the postman will automatically claim the message. That's good for first-time users. Putting a fee is good for first-time users. Otherwise, we recommend to manually claim it. Like, yeah. Bridging ERC20, we are going to provide a canonical token bridge that will rely on this layer. Currently, we recommend using partners, and later on, we recommend using the same bridge UI that will be used for bridging ETH. I personally recommend to claim message manually on yourself. So basically, you trigger a message transfer, and then you go on the receiving layer and you claim your message. For other use cases, like other bridges that are built on top of on Linea native message service, we recommend claiming message automatically. That will be it's much cheaper operationally to execute. I think that's it on the bridge overview. I have one slide on the SDK. Do we have any question? Oh, you're on mute.
Yes. No, I don't think I have there's any questions so far. I think people are just kind of, gas fees, but we can address those at the end. But yeah.
The goal of, just as the goal of fees here is really to have them as low as possible. That's why I'm saying we don't want to take any, Linea doesn't want to take any fee or make any money on top of these fees. That's why we have all this, that's why it's a bit complex as well, but it enables most use cases that are the most efficient for each use cases. The fee that you can see here is super tiny, just to prevent DDoS, basically. The fee that you have in the rest of the fees and the postman fees is really the bare minimum that we need. And in this specific workflow, the additional fees that are not necessary will be refunded to the user. And for the rest, the most efficient is always to claim it yourself. Okay, let's move on to the SDK that is coming soon. It will be an NPM package. It's really for builders only. At the moment, it will contain two main features. First one is smart contracts that will help you build like a bit like when you import OpenZeppelin contract. It will contain contracts that you can use for on-chain or off-chain workflow. First main area is like if you're interested in rollup finalization status. So we'll specifically have interfaces that you can use to interact with the rollup. You can look at the latest finalized state, and you can even prove on layer 1 the state that you have on layer 2. This is expensive on chain, but there are some use case off chain that can be interesting for this. The second thing is that if you want to build like a bridge or a cross-chain feature, in this case we'll expose some interfaces in the message service and some abstract utils that you can use to verify that the message coming from the message service and that the sender on the other chain, on the origin chain, was really the contract you intended to talk to. And in addition, it will it will contain key functions to help dapps and protocols claim their message automatically, and that's for basically what I was talking about here in the specific protocol and dapps claiming messages automatically. So yeah, I think that's basically it. Yeah, I'm done with this first this bridge and SDK.
Yes, very, very cool. This is super exciting. I feel like you're probably here the most equipped to answer questions about just like, I guess, future of Linea engineering. People, I think, have concerns about like scaling once we hit mainnet. I think I want to address two questions, especially for the people who are on our voyages. I think I just got notification our DeFi week will be extended 2 days. So DeFi week, which originally I think was going to end on July 4th, will now end July 6th. I think as part of the whole quest thing, you guys might be seeing gas fees being high and transaction times are slow. This is an intentionally introduced, limit, so that we don't affect Gurley like we did in the first week. So like keep in mind this is like not a real environment. So there's that piece as well. But Julien, did you want to say some words on also about kind of like scalability in L2s and like
sure.
Yeah.
So as you've said exactly, at the moment there is a fixed capacity to the layer 2 that we've set as just a first basis that will look to scale further. And because we have this fixed capacity and everyone's super interested to make some transaction on Linea and participate in the quest, obviously it's like offer and demand, the gas price explodes. And this is why you have this huge gas price and even higher than on layer 1. This is completely decorrelated with the layer 1 gas price and the minimum that we are setting on our side. I've added a graph that is basically the minimum gas price that we enforce, which is like roughly 10% of the layer 1 gas price. And as you can see, so this is in Gwei, right? So and it was like taken 25 minutes ago. So 25 minutes ago, the minimum gas price that we enforce in our platform is like 1 Gwei. And up to 2.5 Gwei, not 1,000 Gwei, right? So really what you can see, the 2,000, 5,000, whatever GUI that you can see at the moment is really offer and demand and the capacity that we have on the network at the moment. So it's really a good sign that we have a lot of activity and people are interested to participate in the quest. Looking forward, obviously we'll try to increase the capacity to make it process even more transaction. At the moment, we are processing more gas than the layer one, so which is already really good. We are processing more gas than layer one, and at the cost that is 15% cheaper from a gas perspective. If we look at, for example, I took just 2 transactions that were happening. So that was 25 minutes ago, so it was 26 minutes ago. This is a block on layer 1 go early. It's taking 1 million gas, 1,000,001 gas. Let's look at so this is the gas cost to verify it, to prove it. The gas cost of so looking at logs, you can see here the block number it refers to on Linea. If we take it here and go, we'll see that the gas used is like 16 million. 16.6 million for 1.1 million. So we are like 15 times more gas efficient than the layer one. And this is already just with the state of this alpha version that we are looking to improve.
Okay, cool. So I mean, in summary, right, we're still much more like efficient than L1, right? So the scale is there. The piece, I think a lot of people are like, oh, give us more, like increase the faucets or increase the limits, stuff like that. That just perpetuates the problem, right?
Exactly, because if we give more money in the faucet, basically people will have more money to transact, and we are giving more capacity, like buying power, so prices are just going to like scale up even more.
This is called inflation.
Yeah, it doesn't like we could give more money in the faucet, but that's not really solving the problem.
Right. And I guess to kind of reiterate the whole purpose of the voyages in the first place, right, is number one, just to give you guys a taste of what apps are out there on Linea already, and kind of celebrate the early partners who have joined us in like making Linea really awesome for mainnet to come. So I appreciate all of your concerns. I do want to say again, community, please, like, in the Discord channels, send like your fervent support and thank you and gratification to our customer success team. Be nice to them. They're working around the clock to help you guys out. Engineers are working overtime too to like get this out. But I don't think we have any more time. It's at the hour. So thank you so much, Julien, for joining. That was a really insightful session. I hope you have a good rest of your day. And everybody else. Okay, cool. See ya.